n1, n2, n3 are integers. Suppose I have a set like this. Will this be a vector space? The field is only integers. It's a vector space. It satisfies all the axioms. This is essentially what you call in physics a lattice. A lattice is a vector space defined on the field of integers. Lattice is discrete set of points, right? So a lattice is actually a vector space defined on the integer field. Okay, so now you can think of, for example, you take what is called a BCC lattice. Body-centered cubic lattice. Body-centered cubic lattice, what is the basis? For example, if you take, okay, let us come back to this a little later. First, let me say that a lattice, you have what is called basis for this lattice is given by these vectors A1, A2, A3, right? These are called direct lattice vectors. Direct lattice vectors. They are not orthogonal. For BCC, for example, if you take BCC, I think A1 is given by 1 minus 1, 1, and A2 is given by minus 1, 1, 1, and A3 is given by 1, 1, minus 1. Is that correct? So essentially, if you have a three-dimensional space, and you have a cubic lattice like this, then the body center of this cube, body center of this cube and body center of that cube. That means one of them will become minus, the other two becomes plus. Okay, so they are the primitive vectors of the body center cubic lattice, but they are not orthogonal, as you can see here. So these are like direct lattice vectors. Now, you can ask a question, can I use Gram-Schmidt procedure and orthogonalize? Now remember, in Gram-Schmidt procedure, you have some inner product divided by another inner product. You will not be in the integer space. So you will get some vectors, but they will not be in this vector space. So you start with the lattice, use Gram-Schmidt procedure, you will go out of the lattice. You will get a point in between two lattice points. So it's not a part of your lattice at all. So Gram-Schmidt procedure will not help you to get an orthogonal vector. And you cannot get any orthogonal basis for this. You have to live with non-orthogonal basis. So in such cases, if I want to extract the component of a vector, I have to define a reciprocal basis. Now how do I define a reciprocal basis? So I have to get, so reciprocal basis so let me call that as capital A1, capital A2, and capital A3. Okay, in solid state physics, you will define this reciprocal lattice as AI dot AJ. Normally in mathematics we define it as delta IJ. But in solid state physics, for reasons of extended abstraction and all that, you define it as 2 pi times delta I. Because we always work with a wave vector which is 2 pi by lambda, frequency which is 2 pi times nu and all that. So this 2 pi times delta I. Now what does it mean? Suppose I want to calculate A1. A1 should be orthogonal to A2 and A3. Correct? I have two vectors A2 and A3. It should be orthogonal to those two vectors. So if I have two vectors, I have to find a third vector that is orthogonal to those two vectors. It should be orthogonal to the plane containing A2 and A3. So it should be proportional to A2 cross A3. A2 cross A3 is the vector that is proportional to both A1 and A2. So A1 is proportional to, I can write A2 cross A2. Correct? Because this is orthogonal to both A2 and A3. But what should be the proportionality constant? I will say some n is the proportionality constant. To fix what is the proportionality constant, I must use the third condition. What is the third condition? Third condition is A1 dot A1 should be equal to 2 pi. That implies n times A1 dot A2 cross A3 is equal to 2. So what is n? N is now 2 pi divided by A1 dot A2 cross A3. So I put that n here. I will get the reciprocal lattice vector as 2 pi divided by A1 dot A2 cross A3 into A2 cross A3. So this is the normalization constant, the scalar into this and so on. So we get other definitions in a cyclic way from here. So the reciprocal lattice vectors that we define in solid state physics is actually a construction from this. And of course, in solid state physics, you have an interpretation that you have a family of planes, a family of lattice planes can be mapped to one point in the reciprocal lattice and so on. So if you use this construction, then you will get reciprocal bases, which will actually, in solid state physics, if you have a BCC as a direct lattice, FCC will be its reciprocal lattice, FCC's reciprocal lattice is BCC, and so on. So essentially, reciprocal lattice or reciprocal basis is a construction which is used when you have a non-orthogonal basis. If you want to deal with non-orthogonal basis and extract components of vector, have another non-orthogonal basis which is mutually orthogonal. This is extremely general understanding of from the point of view of vector spaces, because I will also show you when we meet in the next workshop where we do tensors. You can say that if you have 4 vectors, in special theory of relativity we talk about 4 vectors. If you take 4 vectors, you have something called a contravariant vector and a covariant vector. You can see that if you define a direct vector, direct basis, it will be a contravariant, and covariant will be its reciprocal basis. So a direct basis and reciprocal basis can be interconverted into one another by using what is called a metric tensor. So there is a very general connection to these vector spaces, both from the tensors point of view, from the physics point of view that we have in terms of these non-orthogonal bases. So this is one connection to what you know already. If you view this lattice as a vector space, this direct and reciprocal basis is a requirement of non-orthogonality of the given.